Hello, my name is Tom Walski, and today I'm going to be talking about how to create and manage pressure zones in district meters areas in WaterGEMS. Okay, so let's just get some basic definitions down. What's a pressure zone? Pressure zone is an area in a water distribution system that has a similar hydraulic grade. It's usually separated from other adjacent pressure zones that are going uphill by pumps or by downhill pressure zones through a pressure reducing valve or some other kind of control valve, or possibly a turbine if energy recovery is one of the goals in setting up these pressure zone boundaries. Usually pressure zones are used to manage pressure. If the users in the zone are too low of an elevation, they'll get too high of a pressure, or if they're too high, they'll get too low of a pressure. So this is a way of isolating customers. It's saying, at these elevations, in this part of the system, we want to give a certain hydraulic grade. Related to those, but it's a little slightly different, are district metered areas. These are areas in a water distribution system where all the flows are metered both in and out. The pressure in these zones may also be regulated, but the main thing that distinguishes a district metered area is that the flows are known. Now, the use of these is for water audits and water loss control studies. Now, they aren't necessarily the same, but they have a lot of similarities. For example, not all DMAs are pressure zones, not all pressure zones are DMAs, but some are both. Now, within WaterGEMS, we use the term Pressure Zone Manager to describe the software we have that you can automatically set up, establish, and check out these both DMAs and pressure zones. So one of my later presentations will be about how to create pressure zones. The other one will be how to create DMAs. But really, the logic is the same basically across both of those as far as our software. So that's why we just call it Pressure Zone Manager and not a long name like Pressure Zone and District Metered Area Manager. So the tool we use is Pressure Zone Manager. And Pressure Zone Manager can be found either in the analysis menu or as the symbol that green arrow was pointing to. Now, Pressure Zone Manager, therefore, is used both for managing DMAs as well as pressure zones. You get to it through Analysis Pressure Zone Manager, and it relates to a specific scenario. The current scenario is the one that when you talk to the program and tell it to compute, it will compute based on the scenario that you have selected. Now, what you have to do when you get in there is define which elements are the bounding elements. Which type of elements are going to be used to identify the boundary of a pressure zone. Okay, now this is our default screen telling you what types of elements are used as boundary elements and which ones are always used or only used when they're closed or only used in certain specific instances. So, for example, a pipe is not usually a boundary element, but you may have pipes that are that you're identifying the boundaries by having them be closed. So if you're using a pipe closed as the way to identify the boundaries of a pressure zone, a pipe will only be a pressure zone boundary element if it's closed. Usually, if you have isolation valves on the pipe, you generally prefer to use the isolation valve as the way to close the pipe. But some models don't have isolation valves, so you have to actually close the pipe. Isolation valves, again, are normally open in water distribution systems. There's usually many of them in a water system, and only the ones along the boundary are the ones that we're interested in. They're the ones so that's why we say that the isolation valves are boundaries only when they're closed. On the other hand, some elements, when they're used, they're intended to be pressure zone boundaries. So pressure reducing valves, pumps, those sorts of elements are indeed always boundary elements, unless you specifically change that behavior. Now, at the bottom of the screen here, you'll see that they have the possibility of specifying elements that behave differently than that type of element. So you have maybe all pipes are not considered to be boundary elements, but there may be one pipe that you want to use that pipe to be a boundary element. You may not have an isolation valve element on there, but that's the ones you're going to close. So you can't override the generic behavior of that type of element with the specifics for that particular pipe. Now, before we get into some of the other sessions on pressure zones and DMAs. I thought I'd show some pictures so you have a little background of what they look like. Here's one type of valve that's a control valve that is both a PRV and a flow meter. What it has here is a position indicator on the valve actuator, and it also is measuring the differential pressure across the valve. So if you know the position of the actuator and you know the differential pressure across the valve, you can determine what the flow is. So this is one way that you can have a control element that is both a boundary of a pressure zone and it's also a DMA boundary. This is a close-up of that sensor of determining what the position of the valve is in. And this is just a schematic of showing what a PRV really looks like. Okay, another type of element you might have along a pressure zone boundary might be this type of element that's a PRV and it has a built-in turbine meter. So this thing here has just a regular turbine meter built inside of a pressure reducing valve. And that's kind of a schematic of what that thing looks like. And you may have DMA boundary elements that are simply DMA boundaries. They're not pressure zone boundaries. Here's a turbine meter that's basically counting the pulses as the turbine rotates. This is usually found in smaller pipes. Here's an electromagnetic meter that's used usually as you get into bigger pipes where the turbine meter starts to become a little too expensive. These meters start to become more cost effective in the medium sizes. When you get into the really big pipes and large metering elements, Venturi meter is still one of the best. The price of the Venturi meter doesn't go up dramatically with the size. So in the larger pipes, the standard Venturi meter with the right kind of electronic pickups here for differential pressures become usually the best thing to use. This is a graph I drew years ago, and it's still pretty valid that for very low flows, you may want to use turbine meters. For medium range, the mag meter might be best, and for large flows and large pipes, the Venturi meter may be best. They didn't put specific numbers on this graph because it really varies depending on the situation and the system that you're in. But now we're going to get into the actual mechanics of how you would go about creating a pressure zone, first of all, and then given that pressure zone, how you could look at the results and understand the properties of the pressure zone using the Pressure Zone Manager tool. Okay, here's our example water distribution system. The source is over here in the southwest. The pipes are color-coded right now by diameter, so they'd be 8-inch in the red, 6-inch in the blue, and the green are 3 inches, which would be 200, 150, and 100 in millimeters if you're into those units. Now we did an existing run here, and we color-coded the junction nodes by pressure. So let's look at them this way. So nodes that are blue have pressure between 40 and 60. The magenta are between 60 and 80. Those are the nodes we like. The ones that are below 40 are going to be cyan or even green, and those have too low of a pressure. And the ones that are above 80 are going to be red, and those probably have a little too high a pressure for our goal. So let's look at where we're at here. We see that we have mostly magenta, a few blue, those are good ones. We see some red ones down here. This is a low area in the system. And then we go uphill along the south side here, and we see a bunch of cyan ones, which would indicate the pressures are too low. So we could check the pressure down here at this low spot, and we see that the pressure, when we did a run, was about 89 psi, which is a little on the high side. You may want to reduce that. Meanwhile, we go up here to the top of the hill, and we see that the pressure along these nodes are, let's see, 24, which is not quite what we'd like to see in our system. So we're going to try to create a couple of pressure zones out of this single pressure zone system. We're going to make a reduced pressure zone right in this area to lower the pressure. And then up in this area here, which is a high spot, we're going to try to put in a pump along the line to raise the pressure. So it's again, what defines the pressure zone boundaries are usually going to be closed valves, PRVs going to a lower zone, and pumps going to a higher zone. So let's create this lower pressure zone here. So we're going to go in and zoom in on this zone, and at this junction right here, we're going to install a pump, or PRV rather. This is the reduced zone. So we're going to morph this junction node into a PRV. So we'll go over here and pick out the layout symbol for PRV and drop it on top of this node, and we're going to say, yes, we want to morph that. Okay, now we've created that PRV. Are we done with it yet? No, we have to say what the settings are. In the past, the hydraulic grade length area has been around 210 feet, and we want to lower it somewhere to a more reasonable hydraulic grade, so let's set it to about 170. You want to lower make the steps between pressure zones significant. You don't just want to have a PRV reducing the pressure by 2 or 3 psi. It's really not worth it. Okay, however, now when we create that zone, we still have a backdoor feed here where the water can get in and bypass that PRV. So we're going to have to close the isolation valve there. So we'll zoom in here, find this isolation valve, look at the properties and see that it's now open. So we're going to make that property closed. So we've just created a pressure zone in here. This is a reduced pressure zone in this area. And we can check on that a number of ways. One way is to just run the model and see if we change the colors of those elements. And yes, we've gotten rid of those red elements down here. And if we looked at the flows, or let's look at the hydraulic grade line, we see the hydraulic grade line in this area is green as opposed to the red. So therefore, we've created a lower hydraulic grade line. So this is the reduced pressure zone that we've created. Now to create a higher pressure zone, let's go over to this area here. We'll take this junction node and we're going to morph this thing into a pump. Okay, so we'll go over here and grab our pump element and place it down on top of that junction node and we'll morph it. Now in reality, of course, you wouldn't just install one pump usually. You install a pump station with 2 or so pumps in there so you have backup equipment. But for this simple example, we'll just put one pump there. Now we have to specify the properties of that pump, and this is pretty simple. In this particular case, we check to make sure it's pointing in the right direction, and essentially what we have to do is find the pump curve for it. It's basically the minimum amount of information that you need. So I already inherited the elevation from the junction. So we go in and find that pump definition, which I've already created to move things along. So we've created a pump. It's not going to be a variable speed pump, so we don't have to worry about setting variable speed controls on it. And since there's no storage back here, we're just going to let it run. Now, in reality, you'd probably want to look at a variable speed pump or a hydropneumatic tank here, which is a small boosted zone. But in our case, we're just going to let it run as a constant speed pump. Of course, there's another feed that can get around that pump, and the water can flow back down into the lower zone this way. So we've got to take and close the isolation valve here so that the water doesn't go through the pump and then circulate around back to the suction side of the pump. That would be very wasteful of energy, and I know none of you have things like this in your systems, but every once in a while you find something like this. So we're going to take this pipe and close it there. So now we've created another pressure zone here. This is a boosted zone here. So now let's look at Pressure Zone Manager and see what our Pressure Zone Manager tool can tell us about this. Okay, so we'll find the symbol for Pressure Zone Manager, which is this one, and we're going to pick which scenario we want. We want to look at the entire system, so we'll hit go and see what it calculates. And sure enough, what we have here is a system that has 3 different pressure zones. We can look at which nodes are included. Let's make this a little bigger here. Make this bigger and this a little smaller. And we see that we can see every element that's in pressure zone 1. We can see every one in pressure zone 2 and every one in pressure zone 3. We can see what are the boundary elements between those pressure zones. We see we have PRVs and pumps serving as the boundary elements between these elements. We also have some isolation valves that we've closed. Okay, so pressure zone 1, for example, has a pump going out of it and a PRV going out of it. Zone 2 has a PRV coming into it and pump, and Zone 3 has a pump pumping into it. We can visualize things very nicely by going to this highlighting we have here. So I'll pick the highlighting and we'll look at those zones and see what they look like. And it looks like they are exactly what we wanted. We have the main pressure zone up here in red, and below it we have a reduced pressure zone, which is the blue zone. And over here, starting at the pump and working through, around this isolation valve, we have this boosted zone up to this high area on this side of the system. So that's how we create pressure zones in WaterGEMS. And not only do we create pressure zones, but we can visualize them and their properties with Pressure Zone Manager. Oops. Some other things that we can do in Pressure Zone Manager are, of course, create a report. We can also find elements. We can zoom to a pressure zone. So we pick Zone 3. We can just do a zoom, and it zooms only to Pressure Zone 3. And we'll look at finding an element. So you can pick an element and see which pressure zone it's in. So we'll pick the Find button here, pick this junction node, and we see that junction node happens to be in the green zone, which is where we thought it would be and hoped it would be. So that's some of our properties that we can look at in this particular example. And now we're going to go and show how you might create a district metered area. Just to review where we're at, this is our water distribution system. The source is over here on the southwest side. And it generally is a flat area up here, but there's a low area down in this area, and there is a high area up here on the other side of the system. We wanted to, instead of having one pressure zone, we wanted to put a PRV in here to create a lower pressure zone here, and we put a pump over on the east side of the system to raise the pressures in that zone. So we go to our pressure zone manager tool over here, and we can go through and look at the color code. Look at the results from that. We see we have 3 pressure zones, and we can color code by that. And we see that we have this red main zone, this blue reduced zone, and the green boosted zone. So this system is working pretty well, and that's what we have right now. And let's say we are doing a water audit or just a water loss reduction study. We want to see where's the water being used. Is the water being used about the way we feel it should be within our system? Or maybe we have areas that have a high leakage, which would be indicated for having too much water used according to the water meter as opposed to what you're supposed to be seeing. So in addition to these areas here, which we're also going to assume these are also DMAs as well as pressure zones, we'd like to create a new DMA up here in the north side of the system. So we can probably do that by isolating this part of the system. Okay, so it shouldn't be too hard to do because we only have 2 feeds, so we only got to do 2 things. However, how do we define this? You know, with a pressure zone, you would clearly define the zone by either having a PRV or a pump as the feed, but a DMA doesn't necessarily need a PRV or a pump. So what we usually do, or what I prefer to do with a DMA, is use the general purpose valve as the surrogate for the water meter. So I'll grab a GPV here and take this junction node and morph it into a general purpose valve. Okay, and now this node here, we'll zoom in on it, is now a GPV, and it's pointing in the correct direction. We can look at the properties of it, and there's not too much we have to do except we have to set the head loss versus flow relationship for the general purpose valve, because meters will cause a little extra head loss in the system. So now we've inserted that, and so now we'll have an element that can be used to define the boundaries of that pressure zone. Now what happens though is that when you create a zone like this, you then would generally go back in here and close a valve on the other feed. And if we did that, that would work fine. We could meter the flows into this area. But if there's a big demand here, let's say there's a fire in this zone, we aren't able to use this. We'd have to go out there and manually open this valve. So what we'd rather do here, instead of just closing a valve, is install a PRV that'll normally be closed. We call these sleeper PRVs sometimes. So this valve would just stay closed most of the time, and the feed would go through the general purpose valve, which would meter the water into this DMA. But now, what we want to do is, if the pressure really drops, we want this PRV to open. So we're going to make this element here, this junction node, into a PRV. Grab the PRV symbol, place it over here, morph that, and now we have a PRV feeding this zone. Okay, so the thing we have to do here, though, is be careful it doesn't open. We really don't normally want it open. We want it to be normally closed so that we can meter all the flows in through that water meter. So we have to go in here and set this thing. So we know the hydraulic grade, we can just check it if you want, is about, let's see, 216 feet here. Okay, so we know it's 216. So we don't want this to open until maybe, let's say, it drops to about 180 or so. So we'll go in here and say we want the hydraulic grade line to drop to 180. At that time, this sleeper PRV is going to wake up and it's going to start feeding into the zone. So if you're doing some maintenance along that line by the meter, or whether they have excessive flow due to a fire, this thing will open automatically. So this now defines a pressure zone. So let's get back into the pressure zone manager here, and we'll look at our system. Remember, you go up here to pressure zone manager, or its analysis pressure zone. Okay, so currently we had 3 different pressure zones, but now we're going to go back there and change it. But first of all, let's look at some of our options here. We see that the general purpose valve can be used as the boundary. So we have it set so no matter what happens, the GPV will be a boundary. We could have set it so we would not use it. We'd only use it if it was active, or only use it if it was closed. We're just going to say whenever we have one, that's a boundary element. Okay, we already know that PRVs are always going to be a boundary element unless we change these options. So there's our current behavior, and we'll say, okay, look at the system. And now instead of having 3 pressure zones, we have 3 pressure zones, but the 4th pressure zone is really not a pressure zone. It's really just a DMA. So let's color code by that and do the highlighting by color. And we see that we have now 4 pressure zones, but they're really DMAs. See, we use the word pressure zone very generally here. It includes DMAs. So we have our main pressure zone, the blue one. We have the reduced green one. We have this cyan zone, which is our boosted zone. Then over here we have this DMA, which is not reduced. It is just, it has the same pressures. It's in the same pressure zone as the main zone, but now because of the way we've defined this DMA to be fed by the general purpose valve, it is now showing up as a separate zone in our system. Okay, so we can now know what's going on in here. We can then analyze the system, run the analysis, bring back our pressure zone manager. Now we'll look at one other tool we haven't looked at in the previous sessions, is this flow balance tool. So what we can do now is run this thing, let's do it for the current time step because this is a steady state run, and we can look at the properties of these different zones. And we see in particular things like what the demand is in each of these zones. We see the main zone has the biggest demand, and the other ones are somewhat smaller. We can also check on the range of pressures. Are these range of pressures reasonable? For the most part, they are reasonable pressures. So we have nicely defined a range of pressures using those pressure zones, and we have also identified what the demands are. So not only can we do that, though, but we also have the ability to look at things in an EPS run and look at the volumes of water. Because usually when you're doing these water audits, we're interested not just in the instantaneous water that's used at a given through a given meter, but we want to look at the cumulative use. So we'll set up an EPS run. We've already defined the demand patterns for the system, so that's all set up here. We're not going to go back through that, but we'll run an extended period simulation, and we've used the model here, what looks like quarter-hour increments to define how the run goes, and we'll now have results here for the pressure zones for extended period simulation. So we'll go back into the pressure zone manager. We'll set this to EPS. We'd like the display in the model to also match the pressure zone that we happen to be studying. So we'll go through and we'll run this again, and we'll come up with the 4 zones that we have in our system. And we'll go back up here and look at the flow balance. Now we have a choice here. We've got an extended period simulation run. We can either look at the flows in and out of each of these zones for a given time step, but of more interest to us in this case is what's the total volume over the course of the day that went into and out of each of these zones. So we see that the properties such as the minimum and maximum hydraulic grades in these zones hasn't really changed much. We see that the main zone's around 220 with the low pressures around 190 low heads, and we see that the pressures are in reasonable ranges. We see the elevations in the zones, but now the thing that's different about this is we now see the total volume of water used during a day. So this is very useful when we're doing things like water audits to say, okay, this is what the model says should be used. Now, if we're using a lot more water in one of these DMAs, especially if it suddenly increases, we start to suspect, for example, excessive leakage or maybe a brand new break in that zone by looking at this. And again, we also echo below here what the boundary elements are that feed each particular zone. So with this information now, we have a better handle on doing things like water audits and water loss studies to find non-revenue water.